Hello, we're going to start with the last part of the Module 1, per unit analysis. Well, let's imagine that you have a system where you have those transformers that I mentioned before. So you probably have some medium voltage here, then you are using a transformer to step up from 110 kilovolt to 20 kilovolts. Then there is lines transmitting this electricity to different nodes. Electricity then is stepped down to 30 and 80 volts. The same in this one. So there are 3 transformers in this system. Well, we have learned how to model this transmission line. We know Kirchhoff laws already. We haven't learned how to model a transformer. We'll let you know how to model a transformer just in a few minutes. But you can observe here a very interesting thing. Numbers can be pretty different. For example, I have 380 volts, but also in this circuit I have 20,000 volts. So those two numbers are actually pretty different. They can actually cause some numerical issues, and you can guess that the computer are solving most of the problems on computing what are the flows through the lines and what are the voltage at each node. For computing those values, we will have to implement algorithms, and we know when the numbers are pretty different, we can have some numerical issues. For example, if you want to make an inverse of a matrix, and elements of the matrix are 10 to minus 3, then you have 10 to the 6, 1 and 10 to the 12. So you see there are numbers that they are kind of pretty different. So you can have kind of these numerical issues that doesn't help to do a calculation. So one interesting thing here is to normalize in somehow. And in power system, actually, we can do this in a very smart way. What is this normalization? Is trying to put all the value to some common reference. They are pretty close, so we can transform into this normalization and then come back to the original values. In power system, this is called per unit analysis. Well, per unit analysis or per unit system is this normalization basically for all the values that we can find in a power system, like voltage, current, impedance, or power. This actually will help to have values in very narrow range, and actually that helps a lot with the computers. I will also show you if we have transformers, we can simplify those transformers and they can disappear for the network when they are assumed to be ideal. So we can just say what a per unit quantity, whatever is that, like voltage, a current, and impedance, it will be the value that we have divided by some reference quantity. So we have to find this reference quantity. I'm going to give you an example. Let's assume that you have this circuit, very simple, and then you know like voltage in this impedance and currents are related. So this is the relationship between voltage in one and the current going through this impedance. Well, the thing that we want to do is, well, let's normalize. If we have a number of voltage 1 like 1000, whatever is the 25 degrees, for example, I can normalize by dividing by 100. So this will be 125, right? So I can normalize by a scalar. Whatever is the current, also I can normalize 1 over 1000 over 1000. It will be 1. Right, so I have numbers that they are pretty close. Then what I need is just to choose these values. But it's most important to keep the connection with the physics laws that we have already seen, Kirchhoff laws. And for doing that, we have to find consistency between the base values or those reference values that we are going to choose. For example, if we want to have the normalized or per unit voltage in one equal to the current times the impedance, we will need to normalize as well the impedance, right? But we cannot take any value of the impedance. We need to normalize by this formula. So you see from here, you see like V, capital V, or the big B is equal to reference times little b. And here you see like the capital I is equal to the base value times little I. So if we say, I want to have I times C equal to B1, then if you replace here, then I have IB little I times C, capital C, equal to the base of the voltage times little I, V. So from here you can see, to keep the relationships, like little v is equal to I1 times C times IV divided by BB. So I can replace this thing by per unit impedance. And this is consistent with what are the equivalent of the Ohm's law. So I can say, for example, if I have any impedance, I already choose what are the reference value or the base values for the voltages and currents. So the impedance has to follow this value. So I can say that the base value for the impedance, it should be the value that I've chosen for the voltage divided by the value selected for the current. So you can see like any impedance, when it's divided by its base, it gives you this little c. So this is consistent. The per unit system consists on that. We have to find those base values in such a way that everything is consistent. Here this is again. And the same for other values. For example, if we want to normalize or we want to pass to per unit any average power, so you can choose this base power like a voltage time current. Well, this motivation example is for a single phase circuit. One observation is like this per unit cancel out any kind of dimension that we have from those variables. So it means like our variables are dimensionless. When we add some units, so we add like PU, referring like this is per unit, but we are not adding PU volts because it is not anymore measuring voltage, it's just per unit. Well, how we can do this in three-phase systems? This is the steps that you should follow. You can actually go around and make your own system, but this is the classical way of working in three-phase systems. The first thing is like, well, we are going to choose the reference value for the power, and this is a scalar number. Remember, those base values, those are scalar numbers. And then we choose V base, for example, line to line voltage. Then we also need to calculate what will be the base for the impedance when they are connected in Y, and for the current. With that, we have the four bases that we need to transform any variable of my system into per unit. Just to have consistent values, you need to compute the base in this way, compute the base of the impedance in this way. Well, let me explain you about transformer. We have two sides. One side, in this case in the left, is called primary, and the other side is called secondary. Typically, primary is the source of power, and the secondary is the receiving part of the power. When we are sending power from one side to another side, we are expected to have the same power transfer. In this case, we are assuming ideal transformer, so all power that is sending from one side is receiving to other side. So that means like any power in 1 have to be equal to the power in 2. And for doing so, these two equations have to be satisfied. But we observe here that there is a relationship between voltage in two sides of the transformer and the current. 1 over n represents like for one winding in the left, we have n in the right or in the secondary. So this actually creates an increase of voltage in the secondary and a decrease of current in the primary. And this is proportional for the for this relationship from 1 over n. So let me now to transform in per unit voltage and current in the two sides of the transformer. So the first thing that I'm going to do is like, well, voltage in 1, I divide by some reference value, this base voltage, related with the side of the primary on the left hand side. Similar, I'm choosing another base in the right hand side. So I can transform any value of the voltage in the right hand side. I will do similar thing for the currents in both sides. Well, here there is a trick. If we choose the base of the secondary as n times the base of the primary, we will have very nice properties. Similarly, I can choose the base of the secondary as the base of the primary divided by n. You already can imagine why I'm doing that. And the idea is just to make to disappear this n value. Replacing this into this, you will see that the voltage in 1 in per unit will be always the voltage in 2 in per unit. That is amazing because this actually is making to disappear the transformer. So having voltage equal to the voltage in the primary equal to the voltage in the secondary, we don't need this transformer. We know there is a transformer, but we don't need this transformer when we are going to implement in computational methods. The same for the current. So you already see if I'm replacing this into this. So current in 1 is equal to the current in 2. So while not all transformers are ideal, sometimes you can find transformers models non-ideal. If you find a non-ideal transformer, so you will have equivalent impedance. So let me show you how we can implement this per unit analysis. We have the same system I showed before, and we have transformer 1 is a transformer for stepping up. So it's transforming 110 kilovolt to 20 kilovolts. Well, this typically be a generator on the side of 110 kilovolts, and then we are stepping up the voltage to transfer into other buses. Then transformer 2 and 3 are the same, so we are stepping down from this 20 kilovolts to 38 volts. So how we start? Remember, first thing that we have to do is select the power base. Yes, in this case, I don't have a reference here of some power consumption. This is a very simplified model. If you have reference of the power consumption, try to find units very close to these values. I will assume the consumption is around of 1 megavolt ampere, and then I choose 1 megavolt ampere. Well, the second is choose the voltage base. In this case, because I have those values are typically given like line to line. So I will choose base for 1 is equal to 110 kilovolts. Base in 2 is equal to 20 kilovolts. And base in 3 is equal to 380 volts. Well, the next thing I have to choose the current. So current base is the next. For the first one, it's equal to the base, so 1000 kilovolts. Let me put units divided by the square root of 3 times 120 kilovolts. This is equal to 5.2 amperes. Similarly, the current in 2 is equal to 1000 divided by the square root of 3 times 20. Yeah, this is equal to 28.8. And the base for the 3 is 1000 divided by the square root of 3 times 0.38. This is 1519 amperes. So observe that every time that we have a current in each of these sides, if the current is on the side 1, on the area 1, so we have to divide it by 5.2. The current in this area, this is the area 2, right? This is 1 and this is 3. In that case, we need to divide by 28, and for the last area 3, we have to divide by 1519 amperes. We can compute similarly what are the impedance. I will pass here. For the impedance base, for those that they are connected in Y configuration, we can compute them like this. CV1 is equal to 110 divided by the square root of 3. Yes, this is the voltage for one phase divided by the current, right? And the current base for one is 5.24. This guy is BP1, but instead of giving by line to line, is given by phase. Because I'm just using the reference for the Y configuration. This guy is the current also by phase. Well, we can work similarly for the second one and the third one. Finally, note that we have used here kilovolts. This is amperes. I haven't given you a value, but this is 12.1 kilo ohms.